The objectives of today's lecture will enable you to understand the reactions of alkenes involving epoxidation, ozonolysis, polymerization, and we are going to learn the concept of conjugated, isolated, and cummulated alkenes. The next chemical reaction that we are going to study is called epoxidation. Now, what is epoxidation? Epoxidation is the formation of epoxides. Peracids such as peroxyacetic acid or peroxybenzoic acid reacts with alkenes to form epoxides. Now students, what is epoxide? Epoxides are cyclic ethers. As you know that the general formula of ether is ROR. Since it is making a cyclic structure, therefore it is a cyclic ether called as epoxides. Now this alkene over here, we are having a propane reacts with peroxybenzoic acid in the presence of trichloromethane or chloroform to give epoxy propane, a cyclic ether, along with benzoic acid. C6H5 double bond O OH. Now students, let us look at the mechanism of epoxidation. In the first step, the alkene is going to react with the peroxy acid. Over here, the peroxy acid can carry any alkyl or aryl group. Alkene with its pi bond is going to make a bond with this oxygen atom, and our OH is going to add at this carbon atom. This carbon atom will be deprived of its electronic density and will carry a positive charge. On the other hand, the bond between these two oxygen atoms is going to broken down, and this bond will shift on this oxygen as a complete negative charge. As you can see in this step, this is a transition step in which some bonds are being formed, others are being broken down. Now you can see the positive charge on the second carbon atom because it is making 3 bonds. Now a rearrangement is going to happen over here in which the negative charge which was residing on this oxygen atom is going to abstract the proton over here, making a OH bond. And this hydrogen to oxygen bond is going to broken down and reside on oxygen atom as a negative charge, and that negative charge will make a bond with this positive carbon atom, giving rise to an epoxide. The negative charge is shifted on oxygen, which is making a bond with this carbon. A cyclic structure is formed, a cyclic ether, which is called epoxide, giving rise to a carboxylic acid, R, C double bond O, OH. This R can be alkyl or aryl. So this is how epoxides are formed. Students, the next chemical reaction of alkenes that we have to study is called ozonolysis. As the name suggests, addition of ozone. Ozone reacts vigorously with alkenes to form unstable molozonide. This is the structure of molozonide, in which you can see the ozone molecule have been added across the double bond. This O3 is added across this double bond. It rearranges itself spontaneously to form ozonoid. From molozonide, upon rearrangement, it gives an ozonoid. Now students, the ozonoid that is formed is further reduced. Why? Because it is also an unstable structure. So ozonoids are unstable compounds and are reduced directly on treatment with zinc and water. The reduction produces carbonyl compounds. It can be aldehydes if we are having hydrogen on one side, and it can be ketones if we are having this hydrogen atoms as R groups. Ozonolysis is used to locate the position of double bonds in an alkene, so it can be used as a test for the presence of double bond. The carbon atoms of double bond is changed to carbonyl group. As you can see, this is going to get converted as a carbonyl group. This is the second step in which ozonoid in the presence of water and zinc is going to get converted into any carbonyl compound, which can be an aldehyde or a ketone. Now the hydrogen peroxide which is formed is going to react with zinc. As you know that zinc is a reducing agent. So it is going to abstract one oxygen atom making zinc oxide and leaving hydrogen peroxide as H2O. Now students, let us look at the complete mechanism of ozonolysis and reduction of ozonoid. In the first step, alkene is going to make a bond with the ozone. As you can see, this is the structure of ozone having a resonating double bond between the three oxygen atoms. Now the pi bond is going to make a bond with this oxygen atom over here, as you can see, and the pi bond between these two oxygen atoms is going to broken down and shift on this oxygen atom, giving its lone pair back. In this way the positive charge is going to vanish. The third oxygen atom is going to use its negative charge to make a bond with the next carbon atom, giving rise to molozonide. This molozonide is going to get rearranged in such a way that the carbon-carbon bond is going to broken down, and this bond is going to shift between this oxygen and carbon, making a double bond. The oxygen to oxygen bond is going to be broken down, and this bond will shift on this oxygen as a negative charge. The lone pair is going to make a bond with this carbon atom because its valency was destroyed over here. It is making 3 bonds. In order to satisfy the valency of this carbon, the lone pair is going to shift over here, making a bond, a second bond, which is a pi bond, and this oxygen will get a positive charge because it is making a bond with its lone pair, giving rise to fragments of initial ozonoid. In the second step, students, these fragments that were formed are going to react with each other. If we are going to invert this fragment and write it in this manner, then you will understand the mechanism. The negative charge is going to make a bond with this carbon. The pi bond is going to be broken down and make a bond with this carbon atom. The pi bond between this carbon and oxygen is going to broken down and reside on this oxygen atom as a lone pair. In this way, ozonoid is formed. As the ozonoid that is formed is highly unstable, so it is going to get reduced in the presence of zinc and water. Zinc is going to abstract oxygen, making zinc oxide. And this ozonoid is going to broken down over here, giving rise to 2 carbonyl compounds. One carbonyl compound fragment and the other. It can be an aldehyde or a ketone. Students, the last chemical reaction of alkene that we are going to study is called polymerization. Polymerization is a process in which small organic molecules, which are called monomers, combine together to form large molecules, and the substances that are so produced are called polymers. Here is an example from your textbook in which ethene, n number means any number of ethene, is going to react at a pressure of 100 atm. Why do we need such a high pressure? Because ethene is gaseous in nature. In order to react, we have to bring the molecules close together by applying pressure. At a temperature of 400 degrees Celsius, it is going to activate and form a polymer which is called polyethene or polyethylene. A good quality polyethylene is obtained when ethene is polymerized in the presence of aluminium triethyl and titanium tetrachloride. Students, this n number over here is representing how many monomers that we have used for this polymerization, and it is called degree of polymerization, means how many monomers have joined together to form this polymer. Students, always remember that the polymerization process always needs an initiator. That initiator can be a cation, for example H positive from an acid. It can be an anion, for example OH negative from a base, or it can be a free radical. Over here I am going to give you an example of a cation, H positive from sulfuric acid or any acid. You can see that this alkene is going to abstract a proton from sulfuric acid. It is going to make a bond by breaking its pi bond and making a bond with hydrogen atom. The CH2 is converted into CH3 now. But the other carbon atom is deprived of its valency and getting a positive charge. Another alkene molecule is going to make a bond, breaking its pi bond, making a bond with the carbocation over here and adding to the first molecule. And you can see the chain is increasing. Another alkene molecule is going to add across this carbocation in the similar fashion, and this process is going to continue, giving us a polymer. Students, here are some examples of natural and synthetic polymers and where you can find them. Natural polymers are proteins which are made up of amino acids. Starch and cellulose is made up of monomers of glucose. DNA is made up of monomers of nucleotides. Synthetic polymers are polyethane made up of ethane monomers, polychloroethene from chloroethene, polyphenylethene from phenylethene, and polystyrene or polyester from benzene 1,2-dicarboxylic acid. Now students, let us start the concept of conjugation. The word conjugation is derived from Latin word that means to link together. In organic chemistry, it is used to describe the situation that occurs when the p systems are linked together. What do I mean by saying p system? The p orbitals which are forming the double bonds. Here we are going to study p systems in terms of isolated p systems and extended p system. In isolated p system, it exists only between a single pair of adjacent atoms. For example, in ethene, whereas an extended p system exists over a longer series of atoms, molecules in which we are having alternating double bonds, single bond, double bonds, and so on. The extended p system results in an extension of the chemical reactivity. Let us take an example of 1,3-butadiene, which is a conjugated system. As you can see, it is a diene, so it has two double bonds. The first one is present between carbon number 1 and 2. The second one is present between carbon number 3 and 4. These are the orbitals that are overlapping sideways to make these double bonds, and it seems like the p system is extended throughout this system. This is called a conjugated system. Now let us see what is the difference between conjugated and isolated system. The example of isolated system is 1,4-pentadiene. The double bonds are present between carbon number 1 and 2 and the other one between carbon number 4 and 5. But these p systems are disconnected by this CH2 group which is present in the center. These p orbitals are no longer in conjugation because they are not in a continuity. So this is an isolated system. This double bond between carbon number 4 and 5 is isolated from the double bond which is present between carbon number 1 and 2 due to the presence of CH2 group in the center. So we are not having alternating double bond, single bond in an isolated system, whereas you will find double bond and single bonds alternating in a conjugated system. Students, let us see what are the requirements for the existence of conjugated system. For this, we have to consider the orbitals that are involved in the bonding within the system. The first requirement is a conjugated system requires that there is a continuous array of p orbitals that can align to produce a bonding overlap along the whole system. Let us look at the example of 1,3-pentadiene. The first double bond is present between carbon number 1 and 2. The second is present between carbon number 3 and 4. And it seems like p orbitals are present along a continuous array and they are aligned together. This is the structure of 1,3-pentadiene, in which you can see alternating double bond, double bond and single bond. The result of conjugation is that there are extra p bonding interactions between the adjacent p system. Now this is the adjacent p systems. You can see what is the meaning of extra p bonding interaction. Now look at the p orbitals over here. The normal interaction is between carbon number 1 and 2 and 3 and 4. But there is an equal possibility that these p orbitals overlap sideways between carbon number 2 and carbon number 3. So this p system is going to overlap in such a way that the pi electronic density is scattered throughout the system. So it leads to an overall stabilization of the system, because the pi electronic density is delocalized on the whole system. It is not present only at a single position. It is extended throughout this system, which is going to result in the stabilization of this whole molecule. So conjugation leads to stability. Students, let us see what happens in an isolated system. If a position in the chain does not provide a p orbital, or if the geometry prevents the correct alignment, then the conjugation is broken at that point. You can investigate these differences by studying the following example. Look at the example of 1,4-pentadiene. The first double bond is present between carbon number 1 and 2, and the second bond is present between carbon number 4 and 5. Now in the center we are having a CH2 group. Now students, this CH2 group is sp3 hybridized, whereas the double bonded carbon atoms which are present between carbon number 1 and 2, 4 and 5, these carbon atoms are sp2 hybridized. Therefore, this geometry, the tetrahedral sp3 hybridized geometry, is going to isolate this double bond from this double bond. So we will say that the p orbitals geometry is preventing the correct alignment which is required for the conjugation. That is why it is broken at this point. So we are going to say that this double bond is isolated from this double bond, and the overall system is called an isolated system. Now you will see that like in conjugated system, we are not having alternating double bond and single bond. These two double bonds are separated by two single bonds. So it is an isolated system. Students, let us study what is a cummulated system and compare it with the conjugated system. The example of conjugated system is 1,3-butadiene. This is the structure of 1,3-butadiene, and these are the p orbitals. You can see alternating double bond, single bond and double bond. So it is a conjugated system in which the p orbitals are aligned in such a manner that is extended throughout the system. That is why it is called a conjugated system. Now look at the example of 1,2-propadiene. Now you can see that the double bonds are not in alternating fashion. They are present on the adjacent carbon atoms, double bond and again a double bond. Now these are the p orbitals which are making the two double bonds. Now you know that double bonds are formed by p orbitals by sideways overlap, and the necessity of this overlap is coplanarity. Now look at carbon number 1 and 2. For example, if this is a p system overlapping on y-axis. So the same carbon atom, when it is going to make another pi bond on the other side, now there is no y orbital. So it is going to make the other pi bond with its z orbitals. Now you can see that it is not coplanar. This sideways overlap is between z orbitals and this overlap is between y orbitals. So this is called a cummulated system. Students, let us study some examples of conjugated and isolated system. The first one is 1,3-cyclopentadiene. Now you can see that the double bond is alternating with a single bond and again a double bond. That is why it is a conjugated system. Another example of conjugated system is 1,3-cyclohexadiene. The first double bond is present between carbon number 1 and 2. The second is present between carbon number 3 and 4. And the P system over here is extended on a longer series. That is why it is called a conjugated system. Whereas 1,4-cyclohexadiene is an isolated system. Why? Because between carbon number 1 and 2 you will find a double bond. The third carbon will be sp3 hybridized. 4 and 5 is again making a double bond, sp2 hybridized, and the sixth carbon over here will be sp3 hybridized. So these two carbon atoms are disconnecting these two double bonds. So the P system is not extended, it is isolated. Another example is benzene. You know that benzene is having alternating double bonds and single bonds. 3 single bonds alternating with 3 double bonds. And the p orbitals are scattered on the whole system. That is why it is called a conjugated system. Some other examples. Ethene is an isolated system because this double bond is present between only 2 carbon atoms and is not extended on the system. There are no further carbon atoms to extend this P system. That is why it is an isolated system. Propene is again isolated because these p orbitals are only present between carbon number 1 and 2. 1,2-propadiene is a cummulated system because there are double bonds on adjacent carbon atoms. It is also called alkenes. 1,3-butadiene is having extended p orbitals on the whole system. That is why it is called a conjugated